Okay, so differential growth. We'll have dividends that grow at different rates for the foreseeable future, and then grow at a constant rate thereafter. The most common forms are they're given a series of dividends that are given to us, and we'll use those to calculate the value of the stock. Or we can be given, for example, D0, and be told that it's going to grow at X% for 3 years, and then at some other, usually lower percentage for the foreseeable future. So to value a differential growth stock or a non-constant growth stock, we need to estimate future dividends for the foreseeable future, estimate the stock price when it becomes a constant growth stock, and then compute the total value of those future dividends and the future stock price at the appropriate discount rate or required rate of return. In the example here, we're going to have dividends grow at G1 for some years, and then grow at G2 thereafter. So D1 is just D0 multiplied by 1 plus G, just the same as we've been through. D2 is D1 multiplied by 1 plus G, or D0 times 1 plus G. So we can go out as far as we need to. These problems lend themselves to an Excel spreadsheet. If you have a bunch of different growth rates, an Excel spreadsheet would probably be the best method. So dividends grow, so they continue to grow. So at some point in the future, so we're going on out, just like we described. So and then at some point we shift to our new growth rate. Every textbook is going to, as I showed in my problem examples, every textbook is going to show you actually going one dividend beyond where you need to. So I'm going to show you how the textbook would show it, and then I'll show you how I would actually do it. So this first part is we can value as a sum of a T-year annuity growing at a rate of G1. So in this case, we have G1 and G2. So say that's a 3-year annuity, and we have dividends growing for 3 years at that rate. We could do it with this annuity formula. So it's the value, or P, price of the annuity, is equal to coupon, or the payment, or the cash flow, divided by R minus G, multiplied by 1 minus 1 plus G, divided by 1 plus the required rate of return, and those to the power of, in the example I'm discussing, it'd be 3 years. So the discount rate is not going to change. So then the second part of this is the perpetuity. So this is probably a little bit different than the formula you've seen previously, but we can I'll show you how to do it both ways. So then the price of the perpetuity is we take the constant growth model, so the dividend at that point in the future divided by the required rate of return minus G2, or the second growth rate, and then we take that value and present value it back at the required rate of return for how many ever periods we have. So this gives us a whole formula. So you've probably seen this formula. It's just no different than, there we go. So for example, if we had I'll write it out as is, if it's a 3-year transaction. So it would, I don't know why they don't this should be D. So the so D1 divided by 1 plus R, I use lowercase r, plus D2 times 1 plus R squared plus D3 times 1 plus R cubed plus, in this case, we'll do D4 divided by R minus G divided by 1 plus R, 1 plus R, this would be cubed. So this D4 divided by R minus G gives us P3. So we would add the present values of all those cash flows up and it would give it. So this part is no different, but you can use this growing annuity formula, or you can just calculate your dividends, whatever you choose to do. So we're going to start the next lecture with a differential growth example.